Okay, so this is my first lecture on abelian varieties over finite fields. So I'm going to start by giving you the basic properties of those objects. Some of the things that I'm going to say today would be very technical, but if you're willing to accept those as some kind of black box, you would be able to follow the rest of the course. I know that not everyone has taken a class on algebraic varieties and schemes. So what we are going to do throughout this lecture, we are going to fix a field K, and then we are going to let K bar be the algebraic closure of this field. So in some cases, I'm going to give you some indication on how the theory works, but in most of the cases, I'm going to omit the argument that are involved in the proofs. So let's start with a definition of an algebraic variety. By an algebraic variety over a field K, I'm going to mean a scheme which is defined over K, and I want this scheme to be separated. I want it to be of finite type, and then I want it to be geometrically integral. By geometrically integral, I mean that when you take the base change of this scheme to the algebraic closure field K, then you get a scheme which is integral. And we are going to say that our scheme X is complete if it's proper. So this is going to be a very important property for us today, because many of the properties about abelian variety derive from the fact that they are complete. Okay, so now to the definition of an algebraic group. So what is an algebraic group in our setting? An algebraic group would be a tuple, GMIE. The first element of this tuple would be a K variety, which we call G. The second element of the tuple would be a map M from G cross G to G, which is a K morphism. And as you will see, this will be the group law. The second element is also a map from G to G. Again, this would be a K morphism of algebraic variety. And the fourth element of the tuple is an element, an element in the group which is defined over the field K, and this will be the identity element, the neutral element. And for this tuple to be an algebraic group, we want it to satisfy the following properties. So the first property that we want this tuple to satisfy is the associativity of the group law. So for the group to be associative, we want this commutative diagram, which means that if we have three elements in the group, it doesn't matter in which order we multiply them, we will recover the same thing. So if I take three elements here, and then I start by multiplying the first two elements, and then the third element, or I start by multiplying the last two elements and then the first element, then I recover the same element in G. So that's the associativity of the group law, which we require the map M to satisfy. The second property that we require is the identity element. So having an identity element means that if I take any element in the group and I multiply that element by my identity element G, I recover the element that I started with. So meaning that I take an element here, if I multiply by E, then I recover the element E. And then starting here, if I take an element here and I multiply by E, then again I'll recover that element. So multiplication to the right or to the left give me the same element, X. So that means that E is the identity element in our group law. And the third property that we require is the existence of inverse element. And having an inverse element means that we have this commutative diagram here. So if I start with an element X in my group, and then multiplying that element by its inverse, I'll get identity. So if I take the element and multiply by its inverse, what I recover is the identity element here. So that would be the multiplication to the left by the inverse, and this part of the diagram is the multiplication to the right by the inverse, and in either case, you recover the identity element. So having these three properties give us what we call an algebraic group. Okay. So now an abelian variety, given the definition of an algebraic group, an abelian variety would simply be an algebraic group which is complete as a k-variety. And we are going to say that the fact that this is complete has strong implication for our abelian variety A. Right? Among other things, we would see that the fact that this variety is complete forces it to be a commutative group, hence the name abelian variety here. Okay. And the key ingredient in the proof of the commutativity is what we call the rigidity lemma. And the rigidity lemma says the following. So the assumption are the following. So X is a complete variety. If you give yourself a complete variety X, and you give yourself two arbitrary varieties Y and Z, and then now you consider a morphism of variety F from X cross Y to Z. And the theorem says the following. Suppose that you give yourself a point x0 in X and a point y0 in Y, such that when you take the restriction of F to X cross Y naught, you get the constant map. And same thing when you take the restriction of F to X naught cross Y, you get the constant map. The conclusion of the rigidity lemma is that under those conditions, then you get a map which is constant, which is quite strong as a result. And this is really a consequence of the fact that our our variety X is a complete variety. Okay. So this is going to be the key ingredient in the fact that if we give ourselves an abelian variety, then this abelian variety would be commutative. So the first corollary here is that the first corollary of the rigidity lemma is the following. So give yourself two abelian variety X and Y, and then you let F be a morphism of variety which sends the neutral element in X to the neutral element in Y. Then under those conditions, the corollary says that the map F is automatically a morphism of abelian group, so meaning that it would respect the group structure. And the proof of this result is fairly simple. This is probably one of the few results that we're going to prove, so let's give the proof. So the way you prove this is the following. So you consider consider the map So you consider the following map. So the map goes from X cross Y, X cross X to Y, and you take XY and you map it to f of X plus Y minus f of X minus f of Y. So this is, we call this map H. And then if you do that, then you see that if you take H of X0, this would be the same of H of 0x, and this would be 0 for every X in X, right? And so as a result, as a consequence of the rigidity lemma, you see that H would be the zero map, and this would imply that H is a homomorphism. Okay. So the rigidity lemma is saying that as soon as you have a map of abelian, you have two abelian varieties, which we call X and Y. As soon as you have a morphism of varieties between these two objects, which send the neutral element to the neutral element, then this map has to be a morphism of groups. So it would respect the group structure of these two abelian varieties. So it's a very strong result. And it's a corollary of this result that if you have an abelian variety, then it would have to be commutative. So how do we get that in the abelian variety is commutative in this case? In that case, we consider the following map. So you basically consider the map which send x to minus x. Right, so then we see that this map would have to be a group homomorphism. So it must be a group homomorphism. And for this map to be a group homomorphism, you see that this would mean that X must be commutative. So this is now just pure algebra, and I've left this to you as an exercise. So again, you see those two corollaries are relatively easy to prove if you accept the rigidity lemma. So accepting the rigidity lemma, we see straight away that every abelian variety would have a commutative group structure. And this is something that is going to be extremely useful to us. Okay. So now there are two important results that I'm going to state, which we are going to need a bit later. Again, these results are very technical, so I don't expect everyone in the lecture room to know this concept. So again, if you don't know what this means, again, the only thing you need to do is accept these results as black boxes, and then you'll be fine. So the first result that I'm going to state is the so-called theorem of the cube. Again, this theorem relies heavily on the fact that the fact of completeness of varieties. So in this case, the theorem says the following: give yourself three arbitrary variety x, y, and z, and you assume that x and y are complete. And then you give yourself 3 point x naught, y naught, z naught on x, y, z respectively. And the last assumption is that you have a line bundle on the product of these three varieties such that the restriction of L to x cross y cross z naught is trivial. Same way for the restriction of L to x cross y naught z naught, and the restriction of L to x naught cross y cross z. So if you assume that these three restrictions are trivial, then what the theorem of cube says that then it says that the line bundle that you start with would have to be trivial. So again, this is a consequence of the theorem of cube. And as a consequence of the theorem of cube, you would have the following corollary, which says the following: start with an abelian variety A, and then you consider the three projection of, you take the product of A by itself 3 times, and then you consider the projection onto each of those 3 factors. So Then you take the sum of the projection 2 by 2, and then finally you take the sum of the 3 projection, and then you let L be a line bundle on A. So under those assumptions, the theorem of cubes say that if I take the line bundle L prime, which I obtain by taking the pullback of L by the sum of the projection, and then tensor product with the pullback of L inverse by pi 1, 2, the pullback by pi 3, 1, the pi 1, 3, the pullback by inverse of by pi 3, 2, time this this product here, then I get a line bundle which is trivial. Okay, it's kind of harder to state than kind of visualize, but and the proof of this is actually not, again, so once you accept the theorem of cube, the proof of this result is actually fairly easy. So how does the proof work? So basically consider, so let's consider the restriction to so if you consider the restriction to A cross A cross 0, for example, then what do we get? Then you see, if you take the pullback of your line bundle by the sum of the 3 projection, then this would simply be the pullback of your line bundle by the sum of the first 2 projection. And then if you take the pullback of your line bundle by the sum of the first and the third projection, it would be the same as taking the pullback of your line bundle by the first projection. And then finally, if you take the pullback of your line bundle under the third projection, you would get the trivial line bundle. Right? And basically, what that means is that you see that all those factors would cancel out. So and of course, you can do the same thing with the other projection. With the other 2 restriction. And so as a consequence of the theorem of the cube, just then give you the result. Because in each case, the theorem of the cube tells you that, in each case, the theorem of the cube tells you that this factor will cancel out. Okay. So we are going to use this result to study, we are going to apply this result to the torsion subgroup a bit later, but here is again an immediate corollary of this result, which is the following. So now you apply this result to an Abelian variety. So you let A be an Abelian variety and X an arbitrary variety, and you give yourself 3 map of variety from X to A. So we call these F, G, and H. And then we give ourselves a line bundle L on A. And then the theorem says the following. If I let L prime be the line bundle that I get by taking the pullback of L by the sum of the three maps, time the pullback of L inverse by F plus G, tensor the pullback of L inverse by F plus H, tensor the pullback of L inverse by G plus H, and then finally time these three tensor product, then I get a line bundle, which is trivial. And the proof here is again very simple. All you do here is you apply the corollary that we just proved to this map here. So you consider the map which goes from X to the, this is a type. It's a typo, so this should be A. Yeah, so you consider the map that goes from X to A cross A cross A, and it sends X to F of X comma G of X comma H of X, and then you apply the corollary we proved on the previous slide. If you do this, then you recover this corollary. Okay. The other result that we are going to need a bit later is called the theorem of the square, and it says the following. So the assumptions are that we give ourselves an abelian variety A. We let L be a line bundle on this abelian variety. And then we take X and Y 2 points on our variety A. And we let Tx be the translation by X. So under those assumptions, the theorem of the square says that if you take the pullback of L by X plus Y tensor with L, then you get the tensor product of the pullback of L by Tx times the pullback by Ty. And the way to prove the theorem is to apply the corollary that we just saw to the map, the two constant map F of X, the two constant map of F equal X and G equal Y. Right? So, and the third map would be the identity map on A. So if you apply the theorem to these three maps, then you would recover this theorem here. Okay. So we are going to need these two theorems later. So the theorem of the cube and the theorem of the square. But for now, I'm going to discuss the notion of isogeny for abelian varieties. So in order to give you the definition of an isogeny, I'm going to start with a theorem first, which says the following, or rather a proposition. So let F be a morphism of abelian varieties. Then the proposition says that the following condition would be equivalent. So the first one is saying that your map is surjective and that the abelian variety A and B have the same dimension. So to say that your map is surjective and the two abelian varieties have the same dimension would be the same as saying that the kernel of your map is finite as a group scheme, and then these abelian varieties have the same dimension. And the third equivalent condition here is to say that your map F is finite, flat, and is surjective. So again, those of you who are familiar with algebraic geometry, they would see immediately that these three conditions would be indeed equivalent. If not, then again, you would have to accept this as a black box. And then now using these three equivalent conditions, you can now define what it means for a map to be an isogeny. So the definition would be the following. So you give yourself a homomorphism of abelian varieties, And you would say that this is an isogeny if it satisfies either of the three conditions in the proposition. So meaning that the map, let's say, for example, you know that the map is surjective and that the abelian variety A and B have the same dimension, then automatically you know that this would be an isogeny. And so, the second condition would be that you know that the kernel is finite, a finite group scheme, and then the abelian variety have the same dimension. So that's the definition of an isogeny. And the degree of an isogeny, there are several ways to define it, but the way I'm going to define it here is to say that the degree of this isogeny, when you look at the field of function of your two abelian varieties, then this would be a finite extension of function field, and the degree of the isogeny would simply be the degree of that extension. So one can show that this would be the same as saying that the degree of the map is equal to the size of the kernel of the map F. Okay. So one notion that would be very important later, especially when we start discussing Frobenius homomorphism and endomorphism, is the notion of separability of an isogeny. So I'm going to give this definition, and then I'm going to state one of the most important theorems that relate to this notion. So the definition is the following. So you give yourself an isogeny between two abelian variety A and B, and the definition is the following. You would say that F is a separable isogeny if this finite extension of function field is separable. And you would say that F is a purely inseparable isogeny if this extension is purely inseparable. So if you understand what it means for extension of fields to be separable or inseparable, then this kind of characterize what it means for the corresponding homomorphism or isogeny to be separable or inseparable. And the following theorem is one that is extremely important for us, as we will see later. It basically says that you can always factor an isogeny into a product of two isogeny, one of which is inseparable and the other one is separable. So maybe, so if you start with an isogeny, let's say I call this F, then what the theorem says is that I can always find some abelian variety B and call this H and then call this G. So the theorem says if you start an isogeny between A and C, you can always find an abelian variety B, and then you can always find an isogeny G. G would be inseparable. And then here, this one would be separable. Yeah, so that's the content of the theorem. And not only that, the theorem says that this factorization is unique up to isomorphism. So it's a very important theorem, which we are going to need a bit later when we need to understand endomorphism rings of abelian varieties. It's a theorem that would be crucial in that setting. Okay. So that's the next thing that we are going to discuss now is the torsion, the structure of the torsion group. And we're going to see that torsion, which is defined in terms of multiplication by n by integer map, is a very important object when we need to understand abelian varieties. You would use torsion in the construction of the Tate module, and we know that Tate module captures a lot of information about our abelian variety. Okay, so let me start by saying what we mean by the multiplication by n map. So the setup is that we have an abelian variety A. I forgot to say this. So A is an abelian variety. And then the multiplication by n map is the map which sends x to n times x. Right? So if we have an element, we know that we can always add that element to itself n times. And the multiplication by n map is just this map. And what the theorem says that is if the theorem says the following. It says that if you give yourself an abelian variety A, and you give an integer n, the multiplication by n is an isogeny, meaning that it's a map that is surjective with finite kernel. Right? And the second part of the statement is a bit technical, in that this map would be étal if the integer n is prime with the characteristic of the base field. The second thing we need to know about the isogeny is the size of the kernel, or which is in this case is the degree of the isogeny. And in this case, the proposition says that yeah, so I put the dimension of the abelian variety here, but it should have been in this statement. So if you give yourself an abelian variety of dimension g, then the proposition says that the size of the kernel, which is the degree of your isogeny, is n to the power 2g. Okay. So the proof of this theorem is where we actually use the theorem of the cube, which we stated earlier, but unfortunately, I'm not going to give the proof here, but I did give some indication of how the proof worked for those of you who might be interested in having a look in the lecture notes. So if you need additional questions, you can come and ask questions about it. Okay. So as a corollary of these two propositions, we have the following, which is that we can actually, as a module, we can actually say what the torsion group look like. So if you let A and B the kernel of your multiplication by n map, the corollary says that if you know that the characteristic of your field is prime with n, then the torsion group, the kernel as a group would be isomorphic to two G copies of Z mod NZ. So this corollary tells us what the kernel of the multiplication by n map would look like as an abstract group. And again, this would be useful to us a bit later on when we start talking about Tate modules and its properties. Okay, so as a corollary of what we just described, we are now going to discuss the following important corollary, which says the following. Start with an isogeny F, which has degree n, and then the corollary says that Then there is an isogeny which goes from B to A, such that when you compose G with F, you recover the multiplication by N on A. And then when you compose F with G, you recover the multiplication by N on the abelian variety B. And again, this is also a corollary which is very important, which would be very useful when we want to study the structure of endomorphism rings of abelian varieties, for example. Okay. So for now, these are the things that I want to say about isogenies and the structure of torsion subgroup. And what I'm going to do now is give you the definition of the dual abelian varieties and see some of its properties, which are going again to be useful to us later. So for this, I'm going to start by recalling some definition. The first definition is the so-called the Picard group of our abelian variety, which we here it's pic A. So pic A of for an abelian variety A, pic A is simply the set of line bundle over that variety up to isomorphism. And pic 0 of A would be the subset of those line bundle which are invariant by translation by X for any X in A. And an easy consequence of this definition is that if you give yourself a line bundle on your abelian variety, and then you let phi L be this map. So you let phi L be the map defined by sending X to the pullback of L by X tensor with its inverse. You can show that this is, of course, this is again a line bundle. And then one can easily show that this would be a group homomorphism by applying the theorem of square, which we saw a bit earlier. So using the theorem of square, you see that this map phi L would be a group homomorphism. And we are going to need that a bit later. And now we can define what is the dual of our abelian variety. In order to do this, we introduce the following functor. So for any variety T over K, we define Ft to be the line bundle that are defined on A times A cross T, which satisfy these two conditions. So the first condition is that when I restrict L to A cross T for any point T in T, then I get a line bundle in pic 0 of A. And then the second condition says that if I restrict L to 0 cross T, then I get a line bundle which is trivial. So one can easily show that this is a functor. And then if you look at the point of this functor over K, then you recover pic 0 of A. And the key thing that I'm going to do here is to assume that this F is representable. And if you accept that F is representable, then what you get is that the abelian variety which represents F is what we call the dual abelian variety of A. So the dual abelian variety of A is the abelian variety which represents this functor that we just described here. And as a result of its universal properties, this A dual would come with a universal bundle which we call P. And this universal bundle is defined on A cross A dual. And the name for it is the Poincaré bundle of our dual abelian variety. Okay, so this definition is a bit abstract. Here is a more intuitive, somewhat direct way of looking at this definition. So let's say we start with an ample line bundle, right? So as we saw a couple of slides ago, this map phi L is a group homomorphism, but we can say a bit more about it in this case. Because we know that this line bundle is ample, the theorem of square would force the image to lie into peak 0 of A. And one thing that you can show is that you can show that this map is surjective, and you can show that it has finite kernel. And of course, this kernel has a natural structure of a group scheme. So in other words, what that means is that this map that we just defined would be surjective, but remember that this is essentially a dual. So you have a map which is surjective on peak 0 of A, which is A0 dual, the K point of A0 dual. And so what that means is that it means that an alternative definition of your dual abelian variety, you can view it as the quotient of A by the kernel of phi L. So that's a more intuitive and practical way of constructing this dual abelian variety. And one of the main reasons why this abelian variety is so useful is the following proposition, is in that it allows us to define what we call the dual or the transpose of an isogeny. And it's the content of the following proposition. So you give yourself a homomorphism abelian variety, or simply an isogeny if you prefer. And then you let PA and PB, the line bundle, the Poincaré line bundle, associated to coming with the dual abelian varieties for A and B. Then the proposition says that there is a homomorphism which you call F dual going from B dual to A dual. And this, we call it the transpose of the dual abelian variety. And the second content of the proposition is that this F dual is unique, is the unique homomorphism such that when I take the pullback of the Poincaré bundle by identity map cross F dual, it's the same as pulling back the Poincaré bundle on B by F cross the identity map on B. So it's the unique map which satisfies these universal properties. But the key thing of this statement is the fact that we have this this dual homomorphism here. So that's a very important statement for us. And with this, we can now introduce the notion of a polarization of an abelian variety. So if you have you start with an abelian variety, a polarization of this abelian variety would simply be an isogeny from A to its dual, which is given by a line bundle, which is ample. Right? So in the construction of the dual abelian variety, we just saw that there is a way to define a map phi L from A to peak 0 of A, starting with a line bundle. So a polarization is one such map which is given by a line bundle which is ample. And so the degree of the polarization, since this polarization is an isogeny, we can use the earlier definition of a degree to say what the degree of this polarization is. So in this case, the degree of our polarization would be the degree of the polarization lambda as an isogeny. And together with that, we would have the notion of a polarized abelian variety. So if you have an abelian variety which is equipped with the polarization, then you would call this a polarized abelian variety. Okay. So that's our definition. And of course, with this definition, there's a natural definition of definition of a polarized a morphism of polarized abelian variety. So, and it's the following. So you give yourself two polarized abelian variety, A lambda and B lambda, and you give yourself a homomorphism or an isogeny of abelian variety. Then you say that this is a polarized, a more polarized abelian variety if this diagram commute. So that would be the most natural thing to do if you want to define the notion of a polarized abelian variety. So you require that this diagram commute. And the last thing that I want to say here is that if you would say that your polarization is principal if it has degree 1. So having degree 1 in this case would mean that it's basically an isomorphism. And in that case, you say that you have a principally polarized abelian variety. Okay. So this is the theoretical background that I wanted to say about abelian varieties. What I'm going to do now, so again, all this stuff seems like very highbrow and technical. So what I'm going to do is conclude this lecture with a more concrete example using elliptic curve. So I know that some of you probably saw the definition with the lecture by Wanli. So I'm going to give you a more down-to-earth definition because I want this to be, as I said, I want the course to be accessible to the people who might not have a background in algebraic geometry necessarily. So I'm going to give a very down-to-earth definition, which I hope will complement the lecture note by Wanli, which I encourage you to look at, just to complement what I'm going to say today. So in my definition, I'm going to assume that we have a base field of characteristic different from 2, but there's, this can be removed. But for now, for us, this is fine. So for me, an elliptic curve would be a curve which is given by a cubic. So I want E to be given by y squared is equal to f of x, where f is a cubic. I'm sorry. So for me, a cubic curve is a curve which is given by an equation like this. And for this cubic, I'm going to define the discriminant, delta E, to be the discriminant of the polynomial f. Right? So, and this is what the formula for the discriminant would look like in terms of the coefficient of the cubic. And we are going to say that this cubic is non-singular if our discriminant delta is non-zero. So here is a quick example. If my cubic is in this form, then this is what the discriminant would look like. So to say that this cubic is non-zero would mean that this discriminant is non-zero. Okay. Now, if I have such a cubic, I'm going to say that this cubic is an elliptic curve if the discriminant is non-zero. So the condition for the cubic to be an elliptic curve is if the discriminant is non-zero. And of course, you can translate all of this. There's some kind of more intrinsic definition of this notion, which is the one that Wanli gave yesterday in her lecture. Okay. Now, if we have a cubic, I'm going to recall some fact that you might have seen in your course in algebra. So if, let's say you have a cubic F, and then you have the 3 root to that cubic, then you can always write the discriminant in terms of those roots, right? So this is the formula for the discriminant of the root. So you take the difference of the root pairwise distinct indices to the square, and that's the discriminant of your of the cubic. And so granted this, then you see that your cubic would be an elliptic curve if the discriminant doesn't have any repeated, if the polynomial doesn't have a repeated root. And of course, this is equivalent to saying that the discriminant would be non-zero. Okay. So here are some examples. So you can, I gave 3 examples here. You can quickly check that in each case, the discriminant of the cubic is non-zero, which means that you have an elliptic curve. Okay. And so for just if you were interested in drawing elliptic curve in the real locus of elliptic curve, for example, if you took this curve here and you drew it, this would be the real locus of the curve. Okay. So now we are going to, so the goal, I guess, is that we want to show that this cubic has a group structure to get the first concrete example of an abelian variety. So what we call the homogenization of this cubic is what we get by taking the homogenization of the defining cubic, which would be this equation here. And then if you do that, then you would see that there is only one point at infinity, the point with coordinate 0, 1, 0. So this is the only point at infinity. And we are going to see that this is the point that will play the role of the neutral element in our group structure. And so how do we define the set of rational points on our elliptic curve? It's defined as follows. So again, the running assumption is that our elliptic curve is defined over K. We let K prime be a field which contains K. And then the set of K rational prime is given by taking the K rational point on the projective plane, which satisfy our cubic. Right. So that's how we define the K rational point. And you can make this definition kind of less mysterious if you remember that you can write your projective plane as the union of the affine plane with the line at infinity, right? So we know that the only point at infinity that is on the cubic, the elliptic curve, is this one. So we can rewrite this set of K rational point as follows. So this set of K rational point would be this part here times this. So this would be the point lying in the affine plane, union with the unique point lying at infinity. Right. So now that we define what we mean by the K rational point of our elliptic curve or cubic, we can now define the group structure. But before that, I'm going to give you a very vague statement of what the Bezout theorem is, which said, so again, so this is basically with the undergrad who might be in mind, who might be taking this course. So the intuition that I want to give behind the Bezout theorem is the following, which is that we know that if we start with a polynomial of degree n, and we take the roots of that polynomial in the algebraic closure K, if we count those roots up to multiplicity, we know that the number would be exactly n, which is the degree of our field. And there is a kind of geometric analog of this notion, which is known as the Bezout theorem. And its simplest form, it says the following for our cubic curve. So if you have a field K and you have an elliptic curve over this, if you take a line, then this line, this should be P2. So if you take a line in the projective plane, it should be a 2. So if you take a line in the projective plane, that this line would intersect the curve at 3 points. Okay. So I'm not going to go too much into detail, but it's the intuition behind this that I want you to kind of remember. I did discuss a bit this part in the notes, so with several to explain, give you more content about the statement of the Bezier theorem, so you could look at the notes, and then if you have any additional question, you can always come and ask question, and then I'll be happy to expand on those things that I just mentioned. Okay, so now that we have the Bezier theorem, then we can now define what the group structure is. So again, so we want to define the group structure on all the points that are on the elliptic curve. So we take all the points with coordinate in the algebraic closure. So it would be then, so this would be the set of points that we have. And then the way we define the addition, the law on our elliptic curve is by declaring that the point at infinity is the neutral element of our law. And then we declare that if we have 3 points on that elliptic curve, and those 3 points lie on the same line, then they must sum to 0. So in other words, I'm going to say that the sum of P plus Q is equal minus R. So that's how we define the group structure. So it's often kind of easier to illustrate this by a diagram. So basically what I just explained is the following. If I want to add, I have this elliptic curve, which is in blue, and then I have the point P and Q. And if I want to add P and Q, what I do is that I draw a line going through P and Q. So then I have the third point of intersection, thanks to Bezier theorem. And then I take the reflection of that point with respect to the x-axis, and what I get is the sum of P plus Q. So that's how we, so that's basically the content of this definition for our group structure. So that's the visualization of this addition. So here's one very amusing example. So this is often known as the Euler cubic, and you can actually sum, I mean, you can visually sum the point on the Euler cubic without doing much calculation, right? So for example, if I want to sum minus the point, this point, which is minus 1, 0, with this point 0, 1, this line, we can show that it goes through the point 2 and 3. And then when I reflect this point 2 and 3, then I recover this point, which is 2 minus 3. And then you see that you can, those, these points that I have now, I can basically add them by hand, basically. Okay. Okay, so that's the definition of the group law, and this next theorems tell you what you expect, which is that under this group law that we just defined, we actually get an Abelian group. So that's the content. So yeah, it's an Abelian group, which means that the law is commutative. It has a neutral element. Every element has a negative element, and then of course it is associative, right? So again, usually you can prove all this stuff by using very highbrow geometric, algebraic geometry, but the definition basically by hand that I'm doing here, again, as I said, it's because I want to be mindful of the undergrad student who might be in the course, who are not familiar yet with the notion of with these technical notions. Okay, and this is one reason why it's actually quite fun to work with elliptic curve, is that you can actually really make this group law very concrete. And so how do you compute with the group law of your elliptic curve? This proposition is basically an algorithm which will tell you how you should do this. So you should really think of this as an algorithm to compute an elliptic curve. Right. So the algorithm tell you how to, and if you read the proposition by yourself, you would see how you can implement this on the computer and work with it. So if you start with an elliptic curve and you give yourself 2 points on that elliptic curve, there are basically 3 cases to consider. The first case is if one of those points is the neutral element, i.e. the point at infinity, then you know that adding an element to the neutral element, you will recover the element that you started with. So that's the content of these 2 items. And then if neither of these 2 elements is the neutral element, then you would have two cases. So in the first cases, the 2 would have the same x coordinate, but the y coordinate would be opposite, which would mean that these 2 points are sitting on a vertical line, and so they are opposite of each other, and so you get that the sum is 0. In the other cases, that you would have 2 possibilities, which is that the two points have the same x coordinate and the same y coordinate, which is non-zero. In that case, you would set lambda to be this quantity. And in the second case is that the 2 points do not have the same x coordinate and they do not have the same y coordinate. In that case, you set lambda to be this ratio. And then granted this, then you can now define what the sum of these points are, and that's given by this formula here. And again, you see these are very explicit formulas that you can use to compute with the group law of your elliptic curve. Right. Okay, so we are going to conclude this lecture with some example just to show you how to work with this group law. I think I saw in the exercise sheet that there is some exercise in Sage that maybe you can play around. If this is the first time you encounter elliptic curve, you can play around with Sage by working out those exercises. So the first example is this elliptic curve here. You can check that these 2 are point on this elliptic curve. And then if you want to compute P and Q, we need to take the slope of the line going through P and Q. You can compute that slope to be 1. And then if you use the formula that we have in this our corollary, then you get that the sum of P and Q is the point with coordinate -4, -3. So again, there's enough detail in the lecture note, but it would be fun if you work out these calculations yourself. And the last example that I want to mention is this one. So what if I want to add the point P to itself? In that case, I'm in the situation where my point, the 2 points are the same. So they have the same x coordinate and the same y coordinate. So in that case, this is my slope, which is given by the tangent formula. And then I can compute my point using the proposition that we just saw. And in that case, the point you recover is this one. So there are a few more examples in your lecture note that you can practice with. And as I said, I will always be here to answer any question that you might have. I'm hoping that the lecture for the next lecture will go more smoothly than the one today. But I look forward to seeing you. Thank you. It's talking.